Hello and welcome to another video on journal bearings, and this video is devoted to the bearing forces, namely the integration of the pressure field. So the whole video is about these bearing forces, how to obtain these bearing forces. And the integration is really difficult, and you will see a nice way to solve that problem and to carry out the integration of the pressure field. So when we want to integrate the pressure field, first the question is, in which direction do we want to obtain the forces? Do we want to obtain the Cartesian forces? No, not directly, because everything is nicely formulated in our polar or cylindrical coordinates. So we would like to obtain the bearing forces in, one could say, radial and circumferential direction. What does it mean? If you look at that tiny little figure, our radial direction is the direction indicated by the displacement of the center point of the shaft. So by that distance E that we measure in radial direction. If you look at the pressure field, then the pressure field, it's a field, we will have the pressure field in circumferential direction, and the pressure is always in the direction or opposite to the direction of the surface normal of that surface of the shaft. So for example, if you look at such a line here, at such a distance with our angle theta as before, then you would find the pressure there perpendicular to the surface, which is not quite correctly indicated here in that figure by taking that ray, because that ray starts in the bearing center. However, this is not a big deal for us, because this figure does not reflect reality. It's shown here just for the purposes of drawing and indicating some length angles and so on, but in reality the diameter of the shaft and the inner diameter of the bearing housing are closely the same. So therefore, if you take a ray that starts in the center of the bearing, you would be of course perpendicular to the inner surface of the housing, and you would be almost perpendicular to the surface of the shaft, because the diameters or the radii are not so different, and we always put R sub W, the radius of the shaft, to be equal to R for the inner bearing. So from that pressure field we have to project onto that radial direction for the rigid body displacement of the shaft, or the displacement of the shaft, and this can be done by the cosine of theta. So what we finally get is, let's look at the first term here. We integrate, well, in axial direction from minus b divided by 2 to b divided by 2. Then we integrate over a certain range of theta values, so deviations from that radial direction indicated by the angle gamma. And we project with the cosine function the pressure field. And there is a negative sign because the pressure field acts well on the surface, and we compute the force against that direction, so in radial direction. So this would be the formula. Now you might ask, but why is there that angle theta 1 and theta 2? We have to determine these angles later on. For the moment they just stand for the positive pressure hill, because we want to apply boundary conditions, and now they come into play. We just want to integrate the positive pressure hill, so we want to apply Gümbel boundary conditions. And this is where the Gümbel boundary conditions appear first, namely by limiting the integration to a certain range of theta values, namely to the positive pressure hill. Again, I will show you on next slide or next few slides where the positive pressure hill is located. Now let's introduce here our dimensionless pressure. In order to introduce the dimensionless pressure, first of all, we have to make a change of variables here. The first change of variables now concerns z. We move to dimensionless z, and this means that we have to multiply the dimensionless z. So if we introduce dz here by b divided by 2, and that our integration range or range of integration changes now from minus b divided by 2 to b divided by 2 to minus 1 to 1. Next step would be then the introduction of the dimensionless pressure instead of P here. So we get capital pi for the dimensionless pressure, and all the constants that are needed to obtain a dimensionless pressure are now here. So in the opposite sense, so numerator and denominator have been switched to the definition of the dimensionless pressure. So you find r squared mu and omega in the numerator and c squared then in the denominator. So now we are in place to introduce the short bearing solution we found for the dimensionless pressure, and we adapted to the axial boundary conditions already. Well, that was the last result, or the result on the last slide of the previous video, and then we discussed also the effects that are included here, namely that there is a static pressure effect related to the term minus epsilon sine theta, and there are dynamical effects related to the squeezing of the fluid in radial direction and of the whirl motion in circumferential direction, and the prime here indicates the derivative with respect to dimensionless time tau. Well, this is the thing we have to integrate. There's one integration that we can carry out very easily, namely that integration here with respect to z bar. It's a simple polynomial. If we do the integration, you arrive at z minus the z in third power divided by 3. If you do then the computation, then what you get is 1 minus 1/3, which would be 2/3, and then minus 1 and plus 1/3, and in total, so you arrive at 4 divided by 3, and so in total what you get is minus 4 divided by 3. What you get is then from this constant here, it's instead of 3 divided by 8, we would have just a half rb cubed mu omega c squared. And well, the rest, it's 4 divided by 3. The change in sign is just due to a change in sign of the numerator. Yeah? 4 divided by 3, let's do the computation again. You have 2/3 and you have minus 2/3. So 4 divided by 3. 4 divided by 3. Yeah. And here I used that sign, the leading sign here, to change the sign in the numerator. So this will be the task to integrate that quantity now between theta 1 and theta 2. And what we can see is that the integral we obtain here is somehow a sine theta function, a cosine theta function, and then we divide by 1 minus epsilon cosine theta cubed. All the others are just constants. They have nothing to do with the integration. Same for the second term. We have a cosine theta times cosine theta, so cosine theta squared, divided by 1 minus epsilon cosine theta cubed. So these expressions that we have to integrate, they look very similar. They are composed by harmonic functions, sine and cosine function in a certain power, and we always divide by 1 minus epsilon cosine theta cubed. And that division here makes the integration so difficult. How about the circumferential direction? Well, in circumferential direction, you can do the same reasoning. You have to change just one quantity at the very beginning, namely the cosine theta. The projection is now in sine theta direction, or with sine theta. Then all the computations are the same, except that at the very end, instead of cosine theta, you have to write sine theta here. If you look then at the integrals, then you find you get one time here sine squared, and again a combination of a mixed term cosine theta and sine theta. So the integrals we have to solve all belong to the same family. We have a power of sine, a power of cosine that we multiply, and we divide by 1 minus epsilon cosine theta cubed. And that power is limited to either 2 and 0 or 0 and 2 when it comes to the power of sine and to the power of cosine, or 1, 1, cosine theta, sine theta, the mixed term. Yeah? Okay, let's have a look at this on the next slide in more detail. So this would be the corresponding computation for the circumferential direction. And now we get the force F gamma. And you see the only difference is that you put in sine theta here and there instead of cosine theta. Yeah? And well, then in total, we can sum up with that type of integrals the solution as follows. We put as an abbreviation a 3, here as a subscript, so to indicate the power of the term in the denominator, and the superscripts refer to the power of the sine function and to the power of the cosine function. And what you can see is that for Fr in the radial direction you get the mixed term 1, 1, and you get the term 0, 2 with the second power, so cosine theta squared. And for F gamma, if you look at that term, then you see you get the term in sine squared, so 2, 0, 3, and you get cosine theta, sine theta, you get I subscript 3 and superscript 1, 1. And now we have to solve these integrals. And before we do this, let's talk about the integration limits we have to use in the solution of these integrals. So theta 1 and theta 2 here. Well, as I said, we want to apply Gumbel boundary conditions. Now what we do is we look at the numerator in order to get the positive pressure hill. And the numerator is this expression here. 2 epsilon prime cosine theta 1, 2 minus epsilon 1 minus 2 gamma prime sine theta 1, 2. Well, you just divide by the cosine, you put all the leading factors on the other side, and you get an expression for the tangent of theta 1, theta 2. This one. That was easy. Now you could use your calculator or computer, whatsoever, just compute the arctangent function, and you will find the values for theta 1 and theta 2, right? Well, I had this case with an assistant, even a doctoral student, who spent a lot of time and then came to me because his short bearing module did not work well. There were strange results, and he found out that it has to do something with the short bearing module. And then we looked at exactly that point, and what he did was he take the arcus tangent. And then I asked him, well, are you sure that by taking the arcus tangent, asking your computer just to compute the arcus tangent, you get the positive pressure hill? Well, and the answer is no, you can't be sure. So therefore, let's look in more detail at that case. So theta 1 and theta 2 must be such that positive pressure is integrated. So the question is, where is the positive pressure hill? Look at what you would get. The tangent function looks like this, a classical tangent function. Suppose you have the value, have computed this value, and it sits, for example, here. This would be the value for tangent theta. You would ask your computer then to compute the angle theta. Maybe the computer would say, well, this is the value of theta then. You say, okay, nice. I start here and I will end after a period of pi. So I will end here, and this is my positive pressure hill. And now my question again, are you sure that this is your positive pressure hill? Or couldn't it be that the positive pressure hill just starts here at that point, and then adds there, which would be then over there if you include periodicity of the tangent function. Yeah? So the question is the positive pressure hill here or there? You see some nice numbers. So we will make a case, well, a distinction between several cases, and then we find out where the positive pressure hill is. So the first distinction we make is whether we are here in the positive range of tangent values or in the negative values of tangent values. Let's start with the first case. We have positive values of the tangent theta. Then there are two ways to obtain positive values for tangent theta, namely both the numerator and the denominator must be positive, or both the numerator and the denominator must be negative. So as epsilon is always a positive quantity, it's the radius, we take, or the radial distance, we take epsilon prime as being either positive or negative, and 1 minus 2 gamma prime to be either positive or negative. So either we have both epsilon prime and 1 minus 2 gamma prime to be positive, or both epsilon prime and 1 minus 2 gamma prime both negative. In both cases we will get a positive value for tangent theta. So we are in the upper half of this figure. If epsilon prime is positive and 1 minus 2 gamma prime is also positive, one can be said about the cosine theta and the sine theta to get a positive sign here. Let's take, instead of the sine theta, let's take minus sine theta. Yeah? You can see that if these leading factors are positive, then in order to get a positive pressure here, we need a positive cosine theta and we need a negative sine theta, or minus sine theta to be positive, which means sine theta must be negative. Now let's figure out where are the positive values of the cosine, where are the negative values of the sine. Well, you will agree with me that for the sine it's quite simple. The negative values of the sine function appear between pi and 2 pi. The positive values of the cosine function appear in the first quadrant, so between 0 and pi divided by 2, and then up in the last section between 3 pi divided by 2 and 2 pi. Now there is only one quadrant where both cosine theta is positive and minus sine theta, or sine theta is negative and minus sine theta is positive. And this is the last one, between 3 pi divided by 2 and 2 pi. And therefore, that domain in which for sure there is a positive pressure here must be the last domain here, so it must be fully included inside the range for the angle theta. The angle theta can start a little bit before, it can end a little bit later, but at least that part, so between 3 pi divided by 2 and 2 pi must be included. Therefore, we conclude that we need domain 2 here. Okay, so if your computer, if you give him these values, no? And if your computer says, okay, this is the value of the arcus tangent, then you know you have to check the signs of E prime and the sign of 1 minus 2 gamma prime, and then you have to tell him, well, that's nice, but I would like to start with theta 1 being pi plus that candidate, and I would like to end with 2 pi plus that candidate given by the computer for the arcus tangent. You cannot just trust the computer that his arcus tangent value will match the physics. No, you're stupid, your computer. He doesn't know about physics. Okay, second case. Both are negative. So then we need a negative cosine, and we need a negative minus sign, so a positive sine function. A positive sine function appears between 0 and pi. A negative cosine function appears in the second and the third quadrant, so between pi divided by 2 and pi. point between pi and 3 pi divided by 2. Now I think you understand the reasoning. It's clear that there is one interval, namely the interval between pi divided by 2 and pi, where the sine function is positive. So minus sign is negative, and with that negative term we get a positive sign. And the cosine function is negative. So with the negative sign of e prime we get something positive. So that interval must be fully included in the region of integration, the integration region. So we start with that value here, perhaps given by your computer, and you end up with the value that is larger than pi. So you add pi. So we are in domain number 1. Okay, let's move to the second half of that diagram, to the lower half, and let's take values of tangent theta that are less than 0. Then we must have a change of sign, a different sign in the numerator and then the denominator of the tangent theta expression. Here, this is possible if epsilon is negative and 1 minus 2 gamma prime is positive, or epsilon is positive and 1 minus 2 gamma prime is negative. So let's look at the first case here where epsilon prime is negative. So then we need a negative cosine theta and we need a negative sine theta because we have to consider minus sine theta here. So a negative sine theta is again here between pi and 2 pi. We need a negative cosine theta. So we are in the third quadrant. We are between pi and 3 pi divided by 2. So we are in domain number 4. Here it is. Yeah? So either you directly would get this value, but if your computer tells you that he likes negative values, I don't know what kind of value you will get for your arcus tangent, then you would have to add pi, because you want to start between pi divided by 2 and pi, and to be sure that you really include the full range between pi and 3 pi divided by 2. Last case, epsilon prime is, no, just to check, must be domain number 3, just to check, to make sure that we are domain number 3, epsilon prime must be positive, 1 minus 2 gamma prime must be negative, so the cosine function must be positive, the sine function must also be positive, because 1 minus 2 gamma prime is negative, minus sine is therefore also negative, and sine is then positive. So we are in the first quadrant between 0 and pi. And as epsilon has to be, or cosine theta has to be positive, we are in the first quadrant between 0 and pi divided by 2. Therefore, in domain number 3. Yeah? And that's the reasoning how to obtain the integration limits. Yeah? So really take care of that. Don't trust your computer. He can't now. Yeah? Okay, now how to compute the integrals? Well, computation of that integrals is really difficult, and it was Sommerfeld. And I would say it was typical for that area, so for that time, for that era, that people were able to give substitution for these kinds of integrals. I would say they knew much more, they were much better trained to find the appropriate substitutions for integrals than we are nowadays trained, because now you can do it with symbolic mathematics. Hopefully, I mean, you always also have to think and you guide your computer in symbolic mathematics. That can be quite challenging, but at that time, everything has to be done by paper and pencil. And therefore, they were very well trained to find substitutions. And this is what Sommerfeld proposed. And this is a so-called Sommerfeld substitution to solve these integrals. And what appears to be maybe strange at the first glance is that in the denominator, you do not set 1 minus epsilon cosine theta cubed, because you want to get rid of that denominator, or in second power or whatsoever, but that you start with an expression in first power in the denominator. And then you define the cosine alpha to be, one could say, related to the cosine theta, but divided by 1 minus epsilon cosine theta again. Let's see how this works and why it's sufficient to have 1 minus epsilon cosine theta there. First, let's compute the differentials that we need in order to substitute theta by alpha. Well, to this end, I take the derivative of both sides of that equation. So on the left-hand side, for the cosine alpha, I get minus sine alpha d alpha. And on the right-hand side, I apply the classical quotient rule. So I start with the derivative of the numerator, which is clearly minus sine theta. I multiply by the denominator, 1 minus epsilon cosine theta. Then I take the negative sign. I multiply a second term here. I copy the numerator, minus epsilon plus cosine theta, and I take the derivative of the denominator, which is just epsilon sine minus sine theta, so leading to epsilon sine theta then in total. And I divide by the denominator in second power, so squared, 1 minus epsilon cosine theta squared. And don't forget the d theta here. Well, if you sum up these terms, then you see there is a mixed term in sine theta cosine theta, namely with the positive sign here, and it appears here with a negative sign, minus cosine theta epsilon sine theta. So that term will cancel. The only effect we get is from the first term, we get sine theta 1. And from the second term, we get minus, and minus is then plus, epsilon squared sine theta. So we can write a sine theta there, and we get as coefficients 1 minus epsilon squared with a negative sign, so epsilon squared minus 1, and 1 minus epsilon cosine theta squared, the denominator is just copied. D theta. Okay, so this is for the substitution of the differential. And you can see that for the substitution of the differential, it is required that you take already 1 minus, or that you furnish, I would say, in order to substitute the differential, that you furnish also 1 minus epsilon cosine theta squared. And with this, already 1 minus epsilon cosine theta squared in the denominator goes away. Lose it in the substitution of the differential, or in the replacement of the differential. Okay, now there could be, of course, and will be some terms in cosine theta, in sine theta, and also there is a remaining 1 minus epsilon cosine theta in the denominator possible. So we have to express these terms, cosine theta, 1 minus epsilon cosine theta, and sine theta by appropriate harmonic functions of the angle alpha. Well, for the cosine theta, this is quite simple, because you can solve this equation here, the substitution for cosine theta. And what you get is then the cosine theta is cosine alpha plus epsilon divided by 1 plus epsilon cosine alpha. So you multiply here the whole equation by 1 minus epsilon cosine theta, then this would be the leading coefficient of the cosine alpha. You have another cosine theta there, so you put the term that is epsilon cosine theta on the other side to the cosine theta to get 1 plus epsilon cosine alpha, and then you divide by the leading factor, and the remaining term is then just a cosine alpha from the multiplication of the cosine alpha with the denominator, that one here, and a plus epsilon which goes to the left-hand side, therefore with the positive sign, and then you get this numerator. So this is easy to obtain. Also then, if you have cosine theta, the computation of 1 minus epsilon cosine theta is not difficult, I would say. No, you just multiply the result by epsilon, and instead of 1, of course, you write 1 plus epsilon cosine alpha divided by 1 plus epsilon cosine alpha. You add everything together. You will lose in this way the cosine alpha here, and you get just 1 minus epsilon squared divided by 1 plus epsilon cosine alpha. And for the sine theta, you apply the trigonometric Pythagoras and you express sine theta as being the square root of 1 minus cosine theta squared. And if you then do the manipulations, so instead of 1, of course, in the radicand, you write again 1 plus epsilon cosine alpha squared divided by 1 plus epsilon cosine alpha squared. You add everything together, you take the root, and you obtain the root of 1 minus epsilon squared sine alpha divided by 1 plus epsilon cosine alpha. Now, after these technical details, so the important thing, the difficult thing was to find that substitution. We would like to see how that substitution works in practice, right? So let's take the first candidate, I311. So we have, at the beginning, we had, I would say, a sine theta, a cosine theta, and a 1 minus epsilon cosine theta cubed. You can see I carried out already the substitution. The substitution leads to angles alpha 1 and alpha 2 that can be easily computed, and now without all the story behind for theta 1 and theta 2, it's important, of course, to get the right interval, and then you get, or maybe you want to check that you really get also the right intervals for the angles alpha, but from that equation you can easily compute alpha from theta by taking the arcus cosine function of that expression here and evaluate that expression first and then get the arcus cosine function. Now, how about the substitution here? So the substitution needs a sine theta, so therefore the sine theta does not appear anymore here in the numerator. It needs a 1 minus epsilon cosine theta squared. Therefore, instead of 1 minus epsilon cosine theta cubed, we just have the simple 1 minus epsilon cosine theta. It needs a 1 minus epsilon squared, which we are not able to furnish, so therefore it appears here in the denominator. And then there is, from the left-hand side, the sine alpha here. And, well, as both signs are negative, you can drop that negative signs here on both sides. No? So we get that expression. You see that this is not the end, because this is the mixed expression, and that's why we had to compute these values here. You see there is a sine alpha, which is good, but we still have the cosine theta and the 1 minus epsilon cosine theta, and we want to replace it by terms that include the angle alpha. Now there's one important thing. If you look at these expressions, then you see that the denominator of these expressions is always the same. So if you have a ratio of 2 of these terms, then the denominator will always cancel. And there's another good thing. The only thing that will be in the denominator here is, due to the fact that we lose here the second power, is the term 1 minus epsilon cosine theta. But this is the only term here that does not include any angle alpha, so any sine or cosine harmonic of the angle alpha, in its numerator. The numerator of that expression will of course be the denominator for the expression 1 divided by 1 minus epsilon cosine theta. And with this we avoid to get a harmonic function in the denominator, because that's what causes our problems here. It's not difficult to integrate even powers or products of harmonic functions. But when it comes to the division by a harmonic function, then things become more difficult if you integrate. Yeah? So for analytical integration. So all we have to do is now we have to plug in the expression for cosine theta and the expression for 1 minus epsilon cosine theta. This leads to another 1 minus epsilon squared. So we get 1 minus epsilon squared, which is just a constant for that integration, so which does not make any problems here. And we get in the numerator the cosine alpha plus epsilon, and the two denominators will cancel. So we get sine alpha cosine alpha plus epsilon divided by 1 minus epsilon squared. Here it is. No? And now, well, but this integral is now easy to solve. Either you find it in textbooks or you can do it by hand. A product of sine alpha and cosine alpha between two angles. That's really easy to integrate by partial integration, for example. And the other integral, even easier, it's a constant times sine alpha. Yeah, constant with respect to that integration here. So let's move to the other two cases and check, just make sure that they are of the same level of difficulty at the very end. So again, we take O2 here. So cosine theta squared. We substitute. Unfortunately, when we want to substitute the differential, we do not find a sine theta in the numerator. Therefore, the sine theta appears in the denominator here. And we are left with just one of that 1 minus epsilon cosine theta of the cubed term. And now we have to substitute cosine squared theta, sine theta, and 1 minus epsilon cosine theta. Again, you can see you have the second power here of harmonic functions. You have a second power here of these harmonic functions. So there's no problem with these denominators. They will cancel each other, and this time we have 1 plus epsilon cosine alpha squared, which cancels with again 1 plus epsilon cosine alpha squared. Is there a certain danger that we obtain from the sine theta a sine alpha in the denominator? No, because we are happy to have the sine alpha here from that substitution. It's really conjugated. Yeah? We have the sine alpha here already. So the sine alpha will cancel with the sine alpha that comes from replacing sine theta. So no sine alpha will appear in the denominator. So what remains is, of course, that 1 minus epsilon squared in the square root. And we have the 1 minus epsilon squared here. We have another 1 minus epsilon squared here when we replace the 1 minus epsilon cosine theta, leading to 1 minus epsilon squared in the power of 5 divided by 2, 2.5. Yeah? Twice, once it's here, second time is here, and half is there. Yeah? Okay, how about the numerator? Well, for the numerator, we just have the cosine alpha plus epsilon squared, and that's the result. 1 divided by 1 minus epsilon squared, 5 divided by 2, and cosine alpha plus epsilon squared. And also this integral is then easy to solve by partial integration. Last term. Now we have twice the sine theta. That's nice. We can at least use one of these sine thetas by introducing the differential. So the remaining is just 1 sine theta and 1 times 1 minus epsilon cosine theta. Again, you replace these terms. You can see that you will get another 1 minus epsilon squared here. You have to replace, however, with 1 minus epsilon squared and square root in the numerator, leading now to 1 divided by 1 minus epsilon squared in the power of 3 divided by 2. Okay, just another coefficient, no problem for the integration. And from the sine theta here, you obtain a sine alpha squared. So this is the expression. So 1 divided by 1 minus epsilon squared, 3 divided by 2, and the integral is over sine squared alpha. Okay, and the solutions of the last integrals are stated on the next slide, but you can find it in textbooks, tables, integration tables, or you can do it by hand if you like, just for you to show that no one can obtain these results. And so these 3 integrals are now known. So with this, we know F sub r and F sub gamma, the forces in radial and circumferential direction. And now the last question in this video is, how do we obtain the forces in x and y direction, in Cartesian coordinates, in vertical direction and lateral direction? And this is shown here. It's a classical transformation of vectors. So you did this several times. So you take fx, and I wrote it here in matrix notation. From fr you take the cosine component, or cosine projection on the x direction, and from gamma or F. Is it called F phi or F gamma? F gamma should it be? You take the minus sign projection because F gamma points opposite to the x direction if you project it with the cosine function. For Fy, you take the sign projection of the radial component sine gamma Fr, and you take the cosine projection of F gamma here. Well, and that's it. Now we have the forces. Now we would be already in place to combine or to write a journal bearing module, so subprogram that takes as input E and gamma, E prime and gamma prime, so the rigid body or the displacements and velocities of the shaft, and outputs these forces, perhaps in Cartesian coordinates, F sub x and F sub y. However, for analytical purposes, so in order to analytically, not by numerical methods, combine a rotordynamic model with a bearing module or bearing subprogram, it would be good to consider static equilibrium conditions, so an equilibrium point for the displacements of the shaft, and then to linearize these forces around that equilibrium position in order to obtain stiffness and damping coefficients. And these stiffness and damping coefficients will then be used for a stability analysis for the computation of critical velocities, critical rotational speeds of the rotor. And this is much the same way as we did in machine dynamics, that we compute critical velocities, and therefore we needed stiffness and damping coefficients. So in the next video I will show to you how to obtain these stiffness and damping coefficients. And that's the end of this video. So I hope to see you in the next video. Goodbye to you.